In this problem, we're going to work through setting up and solving a triple integral over a particularly defined region. And in some cases, these are often referred to as type 1 integrals. The reason for that is that the projection of the solid into the xy plane, as I've drawn out here. So the actual sketch that I've created here illustrates the region, in this case D, that we're going to integrate over, and we're presented with a particular surface that's going to bound it. In this case, we're looking at the surface that represents the xy plane on the bottom and the plane z equals y on the top. So that's our surface to surface. The region D is then defined by the x and y bounds here, and that again is given in the xy plane then, because we're looking at the x and y variables. We can identify that a little bit by noting first that the x bounds here are constant to constant, so we know that has to be the outermost integral. And then again, trying to set these up in a way that's most natural, if at all possible. It's best if we can set them up so that the surfaces are stacked vertically. I think that just feels more natural to us. We can think about the difference between the surfaces then as being a bit of an altitude, and we can talk about maybe the volume between them, or whatever it is that we're looking at when we define this solid. So if at all possible, we like to try and set it up so that the x and y represent the region D that we're going to integrate over, what I often call the cookie cutter, and bounds for the surfaces then represent the z. Okay, so let's go ahead and start setting this up. In this case, these algebraic descriptions actually allow us a pretty quick setup for a triple integral. We are given effectively exactly what those bounds are. So we start our triple integral. And for this one, the integrand we're going to work through is 2xyz dv. So this is our integral over our solid E of 2xyz dv. Now let's start throwing some bounds on here. And the way that I often think about doing these again is as two separate schools of thought. So we're going to integrate over our region D, and then on the innermost integral we're going to integrate from surface to surface. So we identified up here the surface to surface is going to go from 0 to y. Our integrand is going to be 2xyz, and now we're integrating with respect to z. This is our first variable, so we'll throw a dz. And I'm going to just box that off so that we know that this is our first integral. And then again, the last part of this is just the region that we're going to be integrating over that we've defined over here in our picture. So from this standpoint, we could actually do this inner integral right now without even setting up the outer two integrals, because that's just a double integral that we would have learned in our previous calculus course, just integrating any double integral like we're familiar with. But we typically do set these things up completely. So let's go ahead and set up the rest of our limits here. We're going to integrate, again, the x values here last, because those are our constants to constants. We always want to make sure that the outermost integral has constants. And that means that the y variables here, or the y bounds rather, and that means that our y bounds here are going to be the next integral. So x to 2x, and then we'll add in our integral from 0 to y of 2xyz dz. Being careful to get our order of integration correct, the next integral would be a dy, and the last one would be our dx. Okay, so we've got the triple integral completely set up. These extra brackets that I put in here are not necessary, really, but I think it does help you visualize and separate out a little bit what's happening with a triple integral when we make the computation. So I will often leave those in for students so that they can see the different pieces of the puzzle coming together. One of the things I really try and emphasize is that we see the triple integral as an integral between two surfaces and a double integral over the region that we're integrating across. I think that helps, again, us really understand what's happening when we're computing these things. So now let's go ahead and do some calculus, and we're going to find some antiderivatives, working as always from the inside out. So we'll first integrate with respect to z. So we would have x, y, z squared, find the antiderivative of z. And we're going to evaluate that from 0 to y. And I'm going to throw on a dy dx out back for the last part of this integral. So let's do that evaluation, 0 to 1, the integral from x to 2x. And if I evaluate z squared at 0 and y, the upper limit first, I'm going to end up with x y cubed after it's simplified. And evaluating at z equals 0 would make this expression 0. So I won't write that down. And let's not forget our notation dy dx. So now we integrate with respect to y. It's just like any other double integral that we would work through. So we'll anti-differentiate the y and evaluate at its limits. That looks like we would have something like 1/4 xy to the 4th. And we're going to evaluate that from, again, x to 2x. And let's not forget our last differential. Okay, valuation, the integral from 0 to 1. Plugging in 2x for the upper limit, I'm going to have 4x to the 5th after it's all simplified, minus the evaluation at x, which is going to look like 1/4 x to the 5th dx. Now this is just a standard single integral. I'm going to go ahead and simplify this down, 0 to 1. I've got 4x to the 5th, and I've got a minus quarter x to the 5th, so that's going to make 3 3/4, or 15/4 x to the 5th dx. And from here, we just go ahead and finish this out, finding the antiderivative. I'm going to have 15 over 24 x to the 6th, and we're going to evaluate from 0 to 1. At 1, it's going to be 15 over 24, and at 0, it's 0. As always, we should probably simplify this down to 5/8. And there's the value of your integral. And like I typically do with my students for problems like these, if it's just a grind it out kind of problem, it's not a bad idea to check your answer in Wolfram or some other computer algebra system just to make sure that you've got it fully correct.